Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Next, we are going to discuss other fundamentals on antenna theory and design, which are the Steradian and Radiant. So I believe that you have heard Radiant, and I am not sure whether you have heard Steradian or not. Right, Steradian, or the abbreviation is SR. It is a square of radian. It is the SI unit of solid angle and used in 3D geometry. Okay, while radian is the SI unit for measuring angles. Okay, steradian for solid angle and the radian is for angle. Steradian can be defined as the solid angle subtended at the center of a unit sphere by a unit area on its surface. Okay, so you have a sphere. Okay, and then you have a surface. Okay, and it's subtended from the center of the sphere. Okay, this will make up a steradian. Okay, a solid angle in steradian projected onto a sphere gives an area on the surface. Okay, so gives an area on the surface projected onto a sphere. Okay, it's projected into a sphere, but this sphere can be represented by a square having the radius equal to r. Okay, for a sphere, we know that the area of a sphere equal to 4 pi r squared. Okay, so in a sphere, there are 4 pi divided by the area equal to 4 pi steradian. Okay, in a sphere. Okay, next is the radian. The 1 radian is defined as the angle subtended from the center of a circle. Okay, for steradian, it is from the center of a sphere, while in radian, it is from the center of a circle, which intercept an arc equal in length to the radius of the circle. Okay, from the center of a circle, which radius is r, okay, intercept an arc. Okay, the red lines represent the arc, which the length equal to the radius of the circle. In this case, the radius is r. The length is r equivalent to the radius of the circle. An angle in radian projected onto a circle gives a length on the circumference. Okay, so for circumference for a circle given by circumference of a circle equal to 2 pi r. Okay, so for 1 radian or for a circle equal to 2 pi r, the total circumference divided by its length, the arc length, equal to 2 pi radian. Right, the infinitesimal area dA on the surface of a sphere radius shown. Okay, this is the surface area on a sphere. So given by, or it can be represented by a square with length of r Okay, if you recall back in mathematics or in the first part of EMT course, so in terms of the coordinate system, when you have a surface on a sphere, it can be represented, the area of this surface can be represented by dA for the area. So in this case, the dA equal to r d theta multiplied with r sine theta d phi. Okay, so therefore the area of the surface on a sphere given by r squared sine theta d theta d phi. Okay, so the element of solid angle or the steradian can be calculated by d equal to the area divided by the surface area. Okay, so in this case, it is equal to sine theta d theta d phi. Okay, for the conversion of radian into degree, so we know that the steradian equal to radian squared. Okay, so radian equal to 180 divided by pi. So therefore, for 1 steradian, it is equivalent to 3283 degrees squared. So this is equivalent to 1 SR. So in a sphere, you have 4 pi steradians. So this is in a sphere. You have 4 pi steradians. So in a sphere, you have 41,253 square degrees altogether. Okay, let's look at an example on steradian. For a sphere of radius r, find the solid angle of a spherical cap on the surface of the sphere over the North Pole region, defined by spherical angles of the given values. Right, so from the previous slide, we know that the steradian equal to dA divided by r squared. What is dA? dA equal to r squared sine theta d theta d phi divided by r squared. Okay, so therefore your d equal to sine theta d theta d phi. So your steradian equal to the integration of sine theta d theta d phi. So sine theta d theta. So the theta given from 0 to 30 degree, and the phi is given by 0 to 360 degree d phi. Okay, so you may write this in gradient, in which the solid angle equal to the phi is from 0 to 360 degree equal to 2 pi d phi, and also 30 degree equal to 0 over pi over 6 sine theta d theta. So then you need to finish up the integration. So in this case, it is equal to 2 pi. So the integration of d phi, okay, multiply with sine, integrate, become negative cos theta from 0 until pi over 6. And then complete your calculation. It is equal to 2 pi times 0.133. So the steradian equal to 0.83566 SR. Well, since the question given it as ohm A, so please use the same notation. It's supposed to be this. Okay, next we are about to discuss on the radiation intensity. So the radiation intensity is the power radiated from an antenna per solid angle. Okay, and it is represented by symbol U, and the unit is watts over steradian or watts over square degree. Okay, if you still remember the solid angle given by d ohm equal to sine theta d theta dV. Okay, radiation intensity U can be briefly described as how bright the bulb may shines. Okay, and the radiation intensity is a far-field parameter given by the following equation. U, the radiation intensity, equal to r squared, the radius of the in spherical coordinates, multiplied by W rad. It is the radiation density in watt per meter squared. Okay, the total power obtained can be calculated by using the following equation, in which P rad, or the power radiated, is the integration of the U, the radiation intensity, multiplied by the unit solid angle. Okay. Okay, for an isotropic source, U, the radiation intensity, will be independent of the angles theta and phi. Okay, and for isotropic source, the P rad is equal to U naught, the radiation intensity of an isotropic source, multiplied by units solid angle. For spherical, for a sphere or for isotropic source, the solid angle may be simplified by 4 pi or 4 pi steradian. So this is isotropic source when the radiation, the maximum radiation, is equal in all direction. Okay, the radiation intensity for isotropic source may be simplified by using this equation: P rad, the power radiated, divided by 4 pi. Okay, let's look at an example on radiation intensity. The question is, if the antenna radiation intensity is given as U equal to R squared, radiation density A naught sine theta, find the total antenna radiated power. So in this case, the question asks you to calculate the P rad, or radiated power. So I would recommend you to write down the general equation before you put in any values or or solve the final answer. Alright, so from previous slide, we know that P rad, or the radiated power, equal to the integration of U d ohm, or the unit solid angle. So in this case, the U is given by A naught sine theta, or U equal to the R squared multiplied by the radiation density. So in this case, it is equal to A naught sine theta, and then the unit solid angle equal to sine theta d theta dphi. And the integration of theta from 0 until pi, and for dphi from 0 until 2 pi. So you need to solve the this integration. So a naught sine theta d theta d phi for theta and also for phi, 0 until 2 pi and 0 until pi. So you should get the p rate or the radiated power equal to pi squared a naught, and radiated power, the unit will be watt. Okay, let's look at next topic on directivity given by the ratio of the radiation intensity U in a given direction from the antenna to the radiation intensity average over all direction. If you look at the example of directional pattern, you can see that this is the area where the maximum radiation is intended. So the D may be simplified as U max, which referred to the maximum radiation intensity divided by U naught, the reference radiation, or U naught also known as the isotropic radiation intensity. Okay, if you still remember from previous slide, the U naught is the isotropic in which the maximum radiation in all or is equal in all direction. So U naught may be calculated by using P rad divided by 4 pi. Okay, for non-isotropic source, the directivity is equal to the ratio of its radiation intensity in a given direction over the isotropic source. Okay, so the D max is the maximum directivity or equal to D naught. Okay, can be calculated by the following equation: U max divided by U naught, in which U naught is equal to P rad divided by 4 pi. Okay, for an isotropic source, the directivity is unity. Okay, because the maximum radiation in all direction equally is equal in all direction. So the directivity is unity or 1. For spherical coordinate system, the total maximum directivity D naught or D max constitute of both the orthogonal theta and phi components, and each component may be defined by the following equation. And in this directivity calculation, you need to consider the vector, okay, in which usually we consider the R. So the maximum radiation, for example, here in R direction. So then the surface it's passed through is in d theta and d phi. Okay, or dA equal to d theta d phi. Let's look at an example on directivity. Okay, write an expression. So an expression meaning that you need to write the equation for directivity as a function of the directional angles theta and phi if the radiated power density, so this is W rad of an antenna, is given by the following equation. So the question asks you for directivity. So the first step is to write down the directivity equation. So D equal to U max over U naught. okay, in which u naught equal to P rad or radiated power divided by 4 pi. So u max multiply with 4 pi over P rad. Okay, next. So given is W rad, so in which u, we know that u equal to R squared W rad. Okay, in this case, W rad is given by that equation. So A naught sine theta divided by R squared. Okay, so u in this case equal to A naught sine theta. So from u, we can determine the u max. Okay, so u max equal to A naught sine theta, in which the maximum radiation happen at theta equal to 90 degree, because sine theta equal to sine 90 degree equal to 1. So in this case, it is equal to A naught sine 90 degree equal to A naught. Okay, next we need to determine what is u naught from P rad. Right, so P rad equal to, again, the integration of u d ohm okay, P rad or radiated power equal to the integration of u d ohm. So u equal to R squared W rad, d ohm equal to sine theta d theta dV. Okay, so from previous slide, W rad is given by A naught sine theta over R squared in the direction of R. So in this case, the W rad is equal to the R A naught sine theta divided by R squared and multiply by the R squared and this sine theta d theta dV, okay, is the, if you have the, this is the maximum radiation direction, so it is in R, the intensity and density in R direction, so the surface the radiation pass through is d theta dV. So in this case, it's normal to the R direction as well. So this is R in R, normal to R direction. So multiply with R squared sine theta d theta dV. So you need to perform the integration from theta equal to 0 until pi and phi from 0 until 2 pi. So this one is equal to the dot product of R. So this is equal to A naught sine theta squared d theta dV. So perform the integration in theta and in phi. So the p rad will get pi squared a naught in what? Okay, so the directivity is equal to u max 4 pi divided by u naught. Sorry, d equal to u max divided by u naught, and u naught equal to p rad over 4 pi. So in this case, u max multiply with 4 pi divided by p rad. Okay, so from the earlier calculation, we have had the u max equal to a naught 4 pi divided by p rad equal to pi squared a naught. So this is equal to 4 over pi. Okay, so the maximum directivity is equal to 4 over pi. Okay, but again, if you refer back to the question, the question asks you to write down the expression of the directivity. So the expression of directivity usually constitute of the maximum, the value of maximum directivity and the angle. So in this case, we can see that the radiation density maximum in theta. So it is d sine theta. In this case, your d is equal to 4 over pi sine theta. So in which the theta depends on the angle of the maximum radiation. Okay, that's another example on radiation in directivity. So please try this out, and the solution is provided as shown. Okay, you've given the W, the radiation density as well, so you need to calculate the directivity, and this directivity basically representing the infinitesimal dipole. Okay, we have seen the example for infinitesimal dipole in previous slide. So in this slide, it is shown the radiation pattern for half wavelength dipole, in which it has the radiation intensity given by A naught sine cube theta, and the directivity is given by 1.67 sine cube theta. And the L for half wavelength dipole, so half wavelength is lambda over 2, and lambda is equal to c over f. C is the speed of light divided by the resonant or the intended frequency of the antenna. Okay, this slide summarizes all equations that we have seen earlier. So the rest are the approximation of the extension of the radiation intensity and directivity based on different types of antenna. Okay, for a directional pattern, besides using the conventional calculation of directivity, it would be much better if you can use a simplified version of the directivity equation, in which the simpler expression to compute directivity when you have directional pattern in which the major loop in one direction, okay, it is narrow major loop in one direction, and the minor loop is almost negligible. Okay, so we can approximate the directivity by using the following equation given by d naught equal to 4 pi divided by ohm A. Ohm A is the beam solid angle, in which it can be approximated by the product or the multiplication of theta 1r multiplied by theta 2r, in which theta 1r and theta 2r is the half power beamwidth in two orthogonal plane. Okay, so 1r for the first orthogonal plane, and the theta 2 for the second orthogonal plane. Okay, for example, if you look at the figure on the right hand side, so if you have non-symmetrical and symmetrical pattern, so you can approximate the beam angle for the orthogonal plane inside the major lobe. So for example, if you have this is your main beam, okay, we can approximate the angles. So this is the first plane. So this is the half power beam width. Okay, the theta, we call it theta R1 or 1R. Okay, and the orthogonal plane that in 90 degree is something like this. So this is theta 2r. Okay, so the beam angle can be calculated by multiplying both the theta 1r and theta 2r. Okay, so the directivity can be calculated by the ratio of 4 pi divided by the beam angle. And for planar arrays, okay, when you have more than one element in your antenna design, so you can approximate the directivity by dividing 32,400 divided by the beam angle, the approximated beam angle. Okay, let's look at an example on the approximation of the directivity. Okay, so when we approximate, the d naught is equal to the 4 pi divided by the beam angle, in which the beam angle can be calculated by the multiplication of the half power beam in one plane multiplied with the other half power beam on the other plane, orthogonal to each other. Okay, so the question given, the radiation intensity of the major lobe of many antennas can be adequately represented by the given equation, where B naught is the maximum radiation intensity. The radiation intensity exists only on the upper hemisphere, given by the following theta and phi angles as shown in the figure. Determine the beam solid angle and the maximum directivity of the antenna. Alright, so we need to calculate or approximate both the ohm A, the beam solid angle, and also the directivity. So the directivity is given by 4 pi divided by the beam solid angle. So we need to calculate the beam solid angle first, in which in this case it is the beam solid angle is the multiplication of both the half power beam in two orthogonal plane. So in this case, this is the first orthogonal plane and the second orthogonal plane, given by the maximum intensity given by cos theta. So we know that half beam power appear at 0.5. Okay, half beam power appears at 0.5, so indicated by cos theta, in which theta equal to 60 degree in this case. So if you still remember, this is the beam width, so theta is only on one side, equal to 60 degree. So the half power beam width in for the first R is equal to 2 times theta, in which 2 theta equal to 120 degree. Right, so this is for the first plane. For the second orthogonal plane, okay, in this direction, okay, this is the second orthogonal plane at 0.5, again at 0.5. So we can assume that the theta to R is equal to 60 degree as well, because the question didn't mention whether the pattern is symmetric or not, so we can assume the pattern is symmetrical. Therefore theta 1R equal to theta 2R, and the first plane is orthogonal to the second plane, so 2 theta 2R equal to 120 degree. Alright, so then the theta A, ohm A, or the beam solid angle, is the product or the multiplication between theta 1R with theta 2R. So in this case, it is equal to 2 pi over 3 multiplied with 2 pi over 3. This is in radian. So you got 4.386 steradian, okay, for the beam angle. And then once you have the beam angle, then you can calculate the directivity. So the approximated directivity given by 4 pi over the beam solid angle, in this case it is equal to 2.865, and in dB it is 4.57 dB. So by using the approximation, the calculation of the directivity becomes much simpler. Okay, same goes to the omnidirectional pattern. You can also approximate the directivity by simply using the approximated equation. So in this case, the intensity for omnidirectional pattern may be approximated by using sine to the power of n theta, and the directivity can be approximated by two given equations, namely McDonald and also Bozar. Okay, the last slide summarizes the equations related to approximation of the directivity. Thank you.